Yours.
All right, thank you, Dr. Miller. Good afternoon, everyone. Good afternoon, committee members, fellow students, guests. My name is Jim Mohr. I'm a master's degree candidate here at the Combustion and Solar Energy Laboratory with Dr. Miller. Today I'd like to present for you some of the results of my research and thesis over the last couple of years. It's titled Modifications to and Modeling of a Lab-Scale Metal Alloy Thermal Energy Storage System, or MATIS. And here's what's going to be presented. We'll start with some motivation. What's the purpose and the importance behind this research? I'll go into MATIS itself. MATIS is both a full-sized concept, but also a lab-scale apparatus that we've developed in order to validate that concept. I'll move into the objectives I assumed at the start of the research. I'll describe some modifications and improvements I made on this lab-scale apparatus. And then the bulk of this presentation will be about the computational model. We chose Fluent as our numerical solver due to its respective performance analyzing fluid flow. I'll describe some expected behaviors that we should see. We should see these behaviors not only in the experimental test, we should also see them in the numerical simulation results, and that'll give us confidence that they're good results. I'll go into estimates of performance, and then I'll present the actual results of the research. I'll then move into, wrap things up with some conclusions and open it up for Q&A. Okay, to begin with the motivation. There's a reasonably well-known curve called the duck curve, and this depicts the net demand on the electrical grid during a typical day in California. And you can see from the blue line there, that's the overall demand on the electrical grid. It's pretty level in the middle of the day. It rises a bit higher in the evening. Then on the bottom there, you can see the power that's provided by solar power. It peaks in the middle of the day, drops off in the evening. Most of the difference between those two curves is the net demand curve, and this is what's called the duck curve, the orange curve there. And it's called the duck curve because it's said to resemble the tail, belly, and the neck of a duck. And the problem, as you might notice, is the overall demand is still climbing in the evening, but at that point the solar power plummets, and that requires a lot of conventional turbines to ramp up to compensate. They have to ramp up by about 13 gigawatts in 4.5 hours. The big problem with this is starting up some of those conventional turbines isn't as easy as switching on the kitchen light. A lot of them are older steam turbines. They take hours to start up. That means they need to be running during most of the day anyway. That means they risk overgeneration and negates much of the benefit of solar power entirely. So this problem here, this big disparity, is epitomized by the duck curve. Although the data I'm showing you is for California, the problem isn't unique to California. It happens all over the world where different civilian and commercial regions are investing heavily in solar power. For example, the state of Hawaii is also investing heavily in solar power. They nicknamed their curve the Nessie curve. The belly of this curve is actually underwater. There's actually more solar power being generated during the day than the demand, and then it ramps up even sharper, resembling the neck of the Loch Ness Monster in the evening. And this brings me to energy storage. If you want to invest heavily in solar power, as a country, for example, and you want to alleviate that duck curve instead of exacerbating it, you need some sort of energy storage, some way you can release and provide that solar power, that green energy that so many societies want, even at times when the sun isn't shining. If you do this, if you have energy storage, it also makes your solar power dispatchable. Now you can supply that energy even at peak times, peak demands during the day, instead of just using it to provide a base load of power. And there's more than one form of energy storage. Thermal energy storage pairs very well with concentrated solar power. When most people think of energy storage, a lot of them think of like electrical storage and batteries, for example. But thermal energy storage is comparably efficient and far cheaper than battery storage. To put some numbers on that, the International Renewable Energy Agency assesses latent heat thermal energy storage as about 75 to 90% efficient, with costs of about $12 to $58 per kilowatt hour. And in comparison to that, one of the world leaders in battery storage today, Tesla, advertises their Powerwall battery storage as also about 90% efficient, but it costs about $437 per kilowatt hour. So it's easy to see that thermal energy storage is comparably efficient and an order of magnitude cheaper than energy storage with batteries.
Can I ask if that depends on scale also, or so lower the $20 to $55 per kilowatt hour? Does that depend on how big the size of the storage?
I would assume it's large scale, like installation size. And Tesla's, their Powerwall, what does that hold? It might hold 10 kilowatt hours, I'm not sure. So it's not as large size as you might use for a power plant, but it's still fairly good size. To add some perspective to this, concentrated solar power right now is about cost competitive with natural gas power, but it's not cheaper than photovoltaic power. And that means if you're looking to invest in solar power, you need to alleviate the duck curve somehow. You need some sort of energy storage. And that means from here on out, thermal energy storage should be considered essential to future concentrated solar power installations. And we're not the only researchers to feel this way. China is investing in developing and building many concentrated solar power plants, and every single one of them currently includes some sort of thermal energy storage. So nearly all concentrated solar power installations today operate on a subcritical Rankine power cycle. The reasons for this are largely due to inherent temperature limitations in the technologies involved. So the current industry standard thermal energy storage solution for concentrated solar power today is the 2-tank molten salt solution. And this works pretty well up until about 600 degrees Celsius, at which point the solar salts begin decomposing and they become useless. And not all installations use that solar salt 2-tank solution. Some use direct steam generation to provide input to their turbine, but that also becomes difficult to control at higher temperatures and starts becoming very difficult to control around 600 Celsius. Beneath 600 Celsius, currently the most efficient power cycle is still the subcritical steam Rankine cycle, and that's why it's so widely adopted in concentrated solar power today. But many experts believe that in the future, to keep concentrated solar power cost competitive with gas power, greater efficiency will be needed from the power cycle, and that will require higher turbine inlet temperatures. Of course, there's more than one way to approach this. Last year, the National Renewable Energy Laboratory, NREL, they published some of their guidance, their Generation 3 roadmap, what they hope is the future of concentrated solar power, and they're hoping to push and guide researchers toward a supercritical CO2 gradient cycle with inlet temperatures over 700 degrees Celsius. So that's what NREL sees as the future of concentrated solar power. I mentioned earlier that the current industry standard solution for thermal energy storage in concentrated solar power today is the 2-tank molten salt solution. But there are some significant drawbacks to it. One of those is the hard temperature limitations. At the lower end, solar salts freeze at about 220 degrees Celsius, and this makes it very difficult to store and retrieve energy, which is the whole point of your thermal energy storage system. At the upper end, they decompose around 600 Celsius, so those are two hard temperature limitations that they're trying to deal with these molten salts. Research is ongoing with other types of salts, such as chloride salts and carbonate blends, to expand those temperature limitations, but that's a work in progress, and it's yet to be seen how fruitful that will be. One of the other big limitations is the low thermal conductivity. Salts aren't really known for having good thermal conductivity. Molten solar salt has a K value of only about 0.5 watts per meter Kelvin. Other salts are similar. Researchers have experimented with different options, such as adding graphite to the salts to form a composite that has a moderately higher thermal conductivity. They've also tried embedding graphite foam or metal matrices in the containers that hold these salts to improve the overall thermal conductivity of the container. But again, this is research, this is a work in progress. It's yet to be seen if solar salts will still be the industry standard solution for high temperature concentrated solar power. This brings me to MATIS. MATIS is an ongoing project here in the Combustion and Solar Energy Laboratory. It originated as a concept to use a metal alloy as a latent heat thermal energy storage solution for concentrated solar power. Latent heat meaning most of the energy is stored and released as it goes through a solid to liquid phase change. There's two big advantages to that. One is that that phase change involves the storage and release of a lot of energy, so the overall energy density of your system could be very high. And the other advantage to that is that most substances go through a phase change at a single temperature, which means most of your energy is stored and released at a single temperature. And that makes it, in theory, isothermal energy storage, which can be very desirable when using it to provide input to a power cycle turbine. After some experimentation, the alloy that was chosen for further study is aluminum silicon. This is a system that's detected at about 12% silicon by molar fraction with a melting temperature of 580 degrees Celsius. It's economical. One of my predecessors, Brian Gehrig, assessed it as roughly 1,300 kilojoules of storage per dollar of material, which is more than any other alloy he considered. It's also more than using solar salt for latent heat thermal energy storage. It's widely available, it's environmentally friendly, it has excellent thermal conductivity at a K value of 160. Those don't melt and freeze at a single temperature, but now across a range of temperatures that extends from the solidus line to the liquidus line. That's called the mushy region because it's not totally solid, not totally liquid. There's one advantage to that. Now you can make the temperature range that you're storing and releasing this thermal heat a little bit tunable. You can extend the range of that upper temperature boundary a little bit by adding a little more silicon. But you now also have the drawback that you're now not dealing with isothermal energy storage. So the full-scale Mantis. Mantis was developed to provide thermal energy storage for a concentrated solar power plant. Two of my predecessors, Brian Gehrig and Dave Curran, really fleshed out and developed this full-scale concept. It would provide thermal energy storage between the small particle heat exchange receiver, or SPARE, which is another project that's ongoing in this lab, and a solar turbine's Mercury 50 gas turbine that can put out 4.6 megawatts of electricity. This system would assume the receiver is capable of heating the air to 1,000 degrees Celsius and sustaining a mass flow rate of 18 kilograms per second. Aluminum silicon 36 was identified as the best alloy for this purpose, and the system as a whole would provide 6 hours of thermal energy storage. It would include 117 cubic meters of aluminum silicon 36 that would be configured in a shell and tube arrangement with 169 rods, each 8 meters long, 26 centimeters in diameter, and with a 5-meter overall shell diameter. And you can see this shell and tube arrangement depicted there on the left. Before such an ambitious project would be undertaken, we wanted to verify it at the lab scale first until this prototype, this lab scale apparatus, was built and developed. You can see a picture from it early in its development there, as well as a cross-sectional diagram of its internals. It's a scaled-down prototype in order to validate the concept. A propane burner with a compressed air supply produces a flow of hot air at 1,000 degrees Celsius and about 20 grams per second. That hot air flows upwards through an annulus in the center to heat a vertical alumina containment cylinder that holds the alloy for stone. Embedded in that containment cylinder, there are thermocouples that monitor the thermal profile during melt and freeze tests on this alloy. It was designed to have roughly the same Reynolds number in the annulus as the full-size version, that is a Reynolds number of about 6,000. And the following couple of slides is what Curran was able to complete at the end of his research and turned over to me at the beginning of mine. Okay, I'll start by describing it from the inside out. At the heart of it is this alumina containment cylinder. Curran first chose alumina after experimenting with several different materials and testing how well they would work as a containment cylinder for aluminum silicon. After running through several thermal cycling tests, he evaluated their cosmetic differences, any weight loss or gain, and he looked for any contamination using microscopy and spectroscopy. After selecting alumina, he created this containment cylinder from the tube 48 inches long, an 1.5 inch outer diameter, and 1/8 of an inch thick. To close up the end of this tube, he also inserted a smaller closed one end tube in the bottom of it and held it in place with a high temperature adhesive. At 1-inch increments along this vertical cylinder, 5 horizontal tubes were inserted and sealed in place with more of this high temperature adhesive. And inside of those were inserted Inconel-clad thermocouples. They were able to monitor the temperature profile at both the axial and radial locations all along the cylinder. So that containment cylinder is at the heart of this. Outside of the containment cylinder is that annulus of hot air. And forming the outer boundary of that is this concrete shell. Refractory concrete is used to form this shell. It's formed into 2 halves. Each half is 55 inches long with a 3-inch outer diameter, 2-inch inner diameter. Embedded in it, at the top and bottom, there's alumina braces which hold this alumina containment cylinder centered in the concrete shell. Also embedded in it, each half has 63 feet of 14-gauge Canthal A1 wire. It runs lengthwise up and down each half of the shell. And the purpose of that is to provide some electrical heating after each experimental test in order to melt and drain the alloy. So the concept of operations for that, after these tests, the entire cylinder would be inverted. A tray of packed sand would be placed underneath. This Canthal wire would then be activated to heat up everything. The alloy would then melt and drain straight down into the tray of packed sand. And that's how we would conclude and clean up after a test. Outside of that concrete shell, there's some insulation, the steel housing, and some external instruments. The concrete shell is wrapped in a 12-foot section of Durablanket S insulation, high temperature insulation. The housing outside of that is built around a Schedule 20 steel cylinder that's 16 inches in diameter and 6 feet long. That cylinder sits in a central pivot so it can be rotated in place, and that pivot is supported by a steel truss stand with caster wheels on the bottom, so the entire system is mobile. The internals inside the cylinder are designed to operate under 5 atmospheres of pressure. And so because of that, this housing also includes 2 very heavy, hermetically sealed lids on either end of the cylinder. The air and propane on the outside are regulated by 2 mass flow controllers. And all these electronics, the mass flow controllers and thermocouples, are connected via USB to a laptop computer, which runs a LabVIEW program that can control, monitor, and log the results of all these tests. So that was the apparatus as Curran completed it and was able to turn it over to me. Here's some of the objectives I assumed when I began with this project. The biggest one was to complete development of this apparatus in order to allow melt and freeze tests to be performed on different aluminum silicon alloys. Unfortunately, towards the end of my time here, towards the end of these developments, a key component, the alumina containment cylinder in the middle, was discovered to be broken completely in half, and that prevented completion on schedule. So because of that, I fell back on a secondary objective, which was to develop a computational model that could estimate the performance and assess behaviors in future experimental tests with this apparatus. We had an existing computational model, but it was not able to provide realistic performance estimates. I'll describe now some of the major modifications I performed to the apparatus. In the interest of time, I had to trim off some of these smaller modifications. One of the big ones was lighter lids were constructed for the apparatus. The original steel lids were 90 pounds each, so it was definitely a strong motivation to construct lighter lids for this.
Should work out more.
Also constructed a temperature control circuit to regulate the temperature on that Canthal wire heating system in the concrete shells. An instrument panel was designed and built to hold these many different electrical and plumbing components. And then I'll wrap this up by describing the current state of the apparatus and what remains to be done. So first of all, some lighter lids. The original steel lids were 90 pounds each. They were difficult for me to handle. I don't know about and it was also discovered, let's see, so they were bulky in order to allow the internals to operate at 5 atmospheres of pressure. But it was discovered to be unnecessary since the thermal behavior of the internals wouldn't significantly change whether between 1 atmosphere or 5 atmospheres. And the thesis goes into more detail on this. I can answer questions on this at the end. But in general, the behavior wouldn't change. Once that was realized, we then began designing and constructing much lighter lids from sheets of 1/4-inch aluminum. You can see a picture of the upper lid on the upper right-hand corner there, and the lower lid with the propane burner and other components. That top lid includes a hole in the center that will let the alloy drain straight down. It includes some steel supports to hold the concrete shell in place while that drain is occurring. And includes some holes for the Canthal wire terminals from the concrete shell to stick out through the lid for easy electrical connection. The bottom lid includes a lot of the original plumbing, includes the jet burner with pilot light, includes a device that provides a distributed air supply called the air sprinkler, and includes an electric igniter.
Jim, can I ask you about the original design pressure? Why was the original pressure 5 atmosphere in the first place?
I'll describe as best I can. Dr. Miller might be able to provide more context. From what I understand, the spare, the volumetric receiver that's also being developed in the lab, operates at 5 atmospheres of pressure. And this was designed to operate at 5 atmospheres because it was thought it would eventually connect to that.
And the sphere is part of the thermodynamic cycle, which operates at high pressure.
Yeah.
It's all related to the high thermodynamic cycle.
Right.
Coupled to that. Coupled.
Exactly. Yeah.
Okay, temperature control circuit. Melting and draining that alloy requires powering the Canthal wires to heat the concrete shell in the containment cylinder past the alloy's melting temperature. So a circuit was designed and built to regulate this process. One of the key considerations in designing the circuit was exactly how much thermal energy is needed to melt and drain this alloy. And this can be approached as a straightforward process. If you take the thermal mass of the concrete shell, the alumina, and the alloy, You multiply it by the temperature difference, about 580 degrees Celsius. You add in then the latent heat of fusion to melt this alloy. You come out to about 8.7 megajoules. So that's the amount of thermal energy we were aiming for to melt and drain this alloy. If you were to hook up one of the halves of this concrete shell to a 120 volt outlet, that would provide about 1,075 watts of thermal power. So if you hooked up each half to a different outlet, you would be able to melt and drain the alloy in about 1.1 hours. We decided that that was a good time frame, wasn't too long, so we proceeded to design and build this circuit. You can see a circuit diagram of what was designed there on the right. At the heart of it is a commercial off-the-shelf temperature controller, the Inkbird temperature controller. There's 2 solid-state relays with heat sinks, 2 ammeters, 1 double-pole safety switch, and everything's held together with 14-gauge wire.
There's an electrical engineer.
Okay, all right, yeah.
So the heating elements are in the concrete.
Correct.
Okay, so the concrete is the heating element. I mean, looks like effectively that concrete shell is what's transferring heat. Okay.
Correct, yeah. Yeah, we've tested this both internally and externally to the cylinder, and we tested up to 250 degrees Celsius, not encountered any significant problems. Instrument panel. So at the start of research, the many components that were used to control and monitor the apparatus were all stored separately, haphazardly connected. To give them a stable platform for operation, an instrument panel was designed and built. You can see the frame for the instrument panel there in the upper right. It's 32 inches long, 15 inches deep, 24 inches high. It's made of half-inch square steel tubing that was MIG welded together. The top is a sheet of 10-inch aluminum, and on the bottom there you can see the finished product with all the components mounted in. In the current state of the apparatus, the cylinder was sealed at the bottom by a cap that was inserted and held in place with a high-temperature adhesive. Unfortunately, that was a very snug fit. It left very little room for thermal expansion. In the early development of this apparatus, there were a lot of combustion trials with different burners that probably produced a lot of uneven combustion, and that produced thermal shock, which we think resulted in the complete failure of the containing cylinder. We've since obtained a closed one-end replacement aluminum cylinder, and replacement and reassembly is in progress.
So that does not rely on a cap.
That's correct.
It's single thickness wall everywhere.
Correct, yeah, you can see, yeah, it's closed at one end, so there's no need to adhere anything onto it.
So the molten salt will be in that, contained in there.
Correct, yeah, that
Not
would,
salt.
Molten salt?
Molten, not salt.
Molten alloy.
Alloy, right, yeah.
So how would you prevent another thermal expansion in the future? Is that
that's a good question. Hopefully this will be, I don't think there's any way to prevent thermal expansion, but we think that the thermal shock that caused it to rupture will be prevented because it's now closed one end instead of having like 2 tubes adhered together.
Maybe point out where it cracked on the upper photo so Tal is clear that, yeah.
That's a good point. Yeah, you can see in the photo the crack line around this outer tube is actually at the same point, the very top edge of that cap that was adhered inside. So that's what we think actually resulted in the fracture of the failure.
Is it wrapped in insulation? Is that what that's? Is it laying on a bed of insulation?
For this picture, yeah, it's lying on a bed of insulation.
I think maybe someone else, I was wondering if it cracked under thermal stress or if any cooling induced extreme thermal stress would be a different issue than just sustaining the heat. That's what I was just curious.
That could be, yeah. We think it probably hit higher temperature gradients in heating than cooling, but it could fracture very cool.
Just curious.
Yeah. Okay, that wraps up the modifications to the apparatus. I'll now get into the computational model that was also developed in the second half of this project. We chose to use Fluent as our numerical solver. I'll first describe a benchmark problem we used to verify the accuracy of Fluent. I'll move into some technical background in Fluent's solidification and melting model, the algorithms and methods it uses, and some of the drawbacks to those. I'll describe some of the expected behaviors that we expected to see. These are behaviors that should not only be seen in the experimental tests, we should also see them in the numerical simulation models, and that'll give us confidence that these are good, accurate results. I'll describe some of the specific properties we use to model the alloys. I'll describe estimates of performance, again, not only for the experimental test, but the numerical solver. and then I'll present the actual results of our numerical simulations. To start with a benchmark problem, we looked to find a benchmark problem that would reasonably resemble the situation we're trying to model. Here we found a problem that involves outward melting of a hollow cylinder due to convection through its center. As far as we know, this doesn't have an exact analytical solution, but it does have an approximate solution which uses the quasi-steady approximation. The quasi-steady approximation assumes the Stefan number is 0. The Stefan number is shown there in the upper right. That's the ratio of sensible heat in a material to the latent heat. If you assume the Stefan number is 0, you're assuming the sensible heat is negligent, and because of that, you can now use the steady state conduction energy equation, which makes the math behind it much simpler. You can see in the lower right there, that's the geometry and boundary conditions we used in Fluent for this test. Remember, for an axisymmetric simulation in Fluent, the x-axis is the axis of rotation. So keep in mind, yeah, it's all rotated around the x-axis. We chose to use an unusually high value of h, about 38,000, and an unusually low value of delta t, 0.1. We did that because with those together, it would produce a heat flux that's comparable to what our final model would use, but it would also keep the delta T extremely low. That would mean the Stefan number is extremely low, which would reduce the inaccuracy of the quasi-steady approximation. We assigned our material properties that were representative of the eutectic alloy aluminum silicon 12. Here's some results from the benchmark tests. We found on the whole the results matched our analytical evaluation. Fluent calculated the melt front after 200,000 seconds is about 6.35 centimeters from the centimeter. The analytical solution found the melt front to be at 6.41. That little discrepancy is expected. The analytical solution used the quasi-steady approximation, so it would slightly overestimate the melt front compared to reality. And you can see plots of the melt front location over time, especially the difference between the analytical and Fluent solution, as well as the temperature distribution and the liquid fraction distribution. We found, on the whole, these results support the validity of using Fluent to analyze axisymmetric phase change problems with convection, which is what our final model would be.
So Jim, you're assuming your initial condition is at 850 Celsius or Kelvin. You specify that everything is at 850 Kelvin except for this heat flux at the inlet.
Right. Yeah, I believe it's 850. I don't know the exact number because we wanted to keep delta T tiny.
Yeah. I
believe we set the melting temperature to 850.75. Our starting temperature is actually 850.7499. And then the delta T is 0.1, so the airflow is then 850.85.
So, so this is not accounting for this transient startup period, or if there is, maybe in the actual energy storage application, this temperature will always be constant for the most. How will the actual cycle coupled to the storage behave? Would it be staying at a pretty much temperature close to this?
Yeah, the temperatures would be close to this. Our final model starts at room temperature actually, and we run 1,000 degrees Celsius air past it until it gets past the melting point. Okay. This test just tests axisymmetric phase change with convection. So we didn't start it with that big temperature difference. We just started it right at the point of phase change for this benchmark.
Okay. Yeah, I agree. So this is just the beginning. We'll go into more detail. Thanks.
Right. Yeah, our final model. Yeah, I'll spend more time describing it. Okay, so I'll get into some of the algorithms and methods Fluent uses in its solidification and melting model. It relies on the enthalpy porosity method, which is a published method that was developed a few decades ago. So when I speak of either the enthalpy porosity method or Fluent, they both have the same advantages and drawbacks. The enthalpy porosity method calculates the liquid fraction of an off-eutectic alloy based only on a linear spread between the solidus and liquidus temperatures. And as many of you remember from your materials classes, that's not the accepted way to calculate the liquid fraction of an off-eutectic alloy in the mushy zone. The accepted way is to use the entire binary phase diagram, draw a horizontal tie line through the point of interest, and then calculate the liquid fraction as a ratio of 1/2 to the whole. You can see in the plot on the low right-hand corner, that shows the disparity between the accepted lever rule and what the enthalpy porosity method does. Because of this big disparity, this affects how accurately Fluent computes the liquid fraction in the mushy zone, as well as all the properties it derives from that liquid fraction, for example, the latent heat of fusion. So that means that Fluent's calculations for the latent heat of fusion distribution through the mushy zone are a bit inaccurate, and because of that, we've looked at different ways we could work around that. We ended up deciding upon an effective specific heat method, which I'll describe later. Another important concept to be aware of with this enthalpy porosity method is a constant called the mushy zone constant. So the enthalpy porosity method includes momentum source terms that dampen velocity in the mushy zone. The idea behind this is that as your substance is cooling from liquid to solid, it's slowly going through that mushy zone, slowly solidifying. You need some way to switch off the velocity and the momentum of the fluid so it stops moving and it freezes in place. That's some of the math that's used here. As you can see, there's an adjustable scaling term, C, right in the middle of it all. The unfortunate part about this is that it's not very well understood what the best value to use for C is. The Fluent User's Guide recommends values between 10 to the 4th and 10 to the 7th, but provides no further guidance beyond that. Many other researchers have looked at this, they've scratched their heads. They're not sure, there's some disagreement about what is the best value to use. A lot of them feel the best value is probably specific to the problem in geometry you're actually working with. Some researchers feel that a higher value, such as 10 to the 8th, produces more physically realistic results overall. And so that's the value that we're going to be using as our default value in these studies. There's some behaviors we expect to see, not only in the experimental test, we should also see them in the numerical simulation results. One of the big ones is natural convection. So natural convection of a fluid with a Prandtl number much less than 1 along a heated vertical wall would include a wall jet, which is an upward flow of fluid from buoyancy, and that would be enclosed inside of a thermal boundary layer, which is a region of elevated temperature adjacent to that warmer wall. If the wall you're talking about is a heated vertical cylinder, the flow usually assumes the form of a warm, rising outer ring of fluid with a cooler sinking core in the middle, and they're able to maintain continuity that way. If you perform a scale analysis of conservation equations, the momentum and energy equations, applied to this geometry and alloy, they suggest that a distinct wall jet will form, but unfortunately the thermal boundary layer would be very large. If it allowed it to naturally develop, it would be so large it would interfere with that cooler sinking core. You can put some numbers on this for values typical of the eutectic alloy midway through a melt with a delta T of 20 degrees Celsius and unimpeded height of 20 centimeters. The Rayleigh number comes out to about 10 to the 7th. The peak of that wall jet would be at less than a millimeter, it'd be right next to the wall, 0.75 millimeters. But the thermal boundary layer would extend almost to the center of the tube. It would extend a full 1.24 centimeters. And so with this in mind, it's not really clear how that will affect the overall heat transfer. We should see fluid flow from natural convection, but it's not really clear how that will affect the heat transfer. It may just be the same as it would from conduction alone.
Is it in the, this is because you're oriented vertically?
Yeah, the equations and everything I'm describing are for heated vertical walls. In our case, it's a heated vertical cylinder, but a lot of the same principles apply.
So this problem would be less controllable if it was horizontal. It would be more of a sticky, like a harder geometry to analyze.
Yeah, at that point it would start forming plumes that rise up separately. For a heated vertical wall, it's, I guess, more straightforward to analyze. It has more well-defined boundary layers and wall jet sizes.
Yeah, if it's horizontal, we lose the
We expect to see solid sinking behavior. So all the alloys we're studying are more dense in their solid phase than the liquid phase. And that means that as they're melting, the unconstrained solid alloy should continually sink in the cylinder as it's slowly melted from the bottom up. And this would produce a flow of warmer fluid around the bottom. It would go up the edges and pool up on top. You can see an exaggerated depiction there of what our containment cylinder might look like. One of the unfortunate things we discovered, though, is that Fluent is not capable of accurately modeling this behavior. The reason I've heard given is that it's very difficult to simultaneously solve the many fluid momentum equations while also accounting for that bulk movement of the solid. Many researchers have looked at this. Some have found like COMSOL produces slightly better results. At least one researcher has given up entirely. He's found he had to model everything with his own custom solver just to get this behavior to actually accurately reproduced.
Sure, that was easy to code. Sure.
Yeah, well, he details it very well, but it took him a lot of effort, I'm sure. And so because Fluent, as far as I understand, is not capable of accurately modeling this behavior is not included in this computational model.
So the solid just sits there.
In our case, yeah, the solid sits at the top, just in place. And it melts from the bottom up.
Yeah.
How fast is that sinking?
Well, how fast should it be sinking for ours?
Like, can you make an argument that, oh, this liquid is so dense that it keeps the viscous force keeps it up, or something like that, within the time scale that we're interested in?
That's a good question. I don't think the viscosity is very high in our liquid metal. The density there's only a slight difference in density between solid and liquid, but I didn't actually do the pencil and paper calculations of how quickly it should sink.
Yeah, gut feel is it's important,
Okay.
but it's a good question. I think we could probably just model a sinking, not melting, but just a sinking thing in the tube, and just on paper, basically. Yeah.
Yeah. Going along with the solid sinking behavior, there's another behavior called close contact melting. So as that cooler sinking solid remains in close contact with the base of the cylinder, which is the hottest part of the cylinder, that would form a very sharp temperature gradient, and that interface can greatly accelerate the heat transfer and the overall melting rate for the test as a whole. Unfortunately, as you might imagine, because Fluent can't accurately model the solid sinking behavior, we don't believe it can accurately model this close contact melting behavior either. And so because of that, close contact melting is also not included in the computational model. Although the solid sinking behavior might have formed a minor change to the overall heat transfer, we think close contact melting would form a more significant boost. And so we feel because of this, the melt times that we predict with this model should be considered as a conservative estimate. Experimental melt tests may very well proceed faster than are estimated here because of the inclusion of close contact melting. So here are some details of the metal alloys we chose to model. We chose 4 different alloys: aluminum silicon 12, which is 12% silicon by molar fraction. That's eutectic. And then 3 hypereutectics: aluminum silicon 20, 30, and 40. The values we used for the various properties are shown there. We had trouble finding the properties of them in liquid state. Those aren't easily available in the literature just because it requires such high temperatures just to measure them at all. And I should also note that we treated the density as constant in both solid and liquid state, constant and equal in both solid and liquid state. The reason for that is if we wanted to include changing density, that would mean our alloy would have to change volume. We couldn't use fixed geometry for it. We would need to include a free surface in Fluent that could go up and down. We weren't able to get that working. That would require Fluent's volume of fluid model. We couldn't get that to converge. We abandoned that and instead decided to model them as being constant density. We don't feel that would significantly affect the results. And although I'm describing them as being modeled with constant density, they did include the Boussinesq approximation, which enables the modeling of natural convection. In addition to those properties of the alloys, I mentioned earlier that Fluent calculates liquid fraction and so the distribution of latent heat of these alloys inaccurately. The way we chose to work around that is with an effective specific heat method. That works by setting the latent heat of fusion to 0 in Fluent and instead artificially boosting the specific heat value of the alloy to compensate for that. You can see a formula in the upper right-hand corner there. That shows how the effective latent heat can be calculated. That's the total latent heat times the change of liquid fraction over a certain change in temperature. And we chose to apply that as a piecewise linear function. You can see a plot depicting those results in the lower right. That blue line at the bottom, that's the effective latent heat as it's crossing the mushy zone. The constant orange line, that's the regular sensible specific heat. If you sum them together, you get the total effective specific heat, and that's what's actually entered into Fluent as the specific heat of the alloy. One thing I should mention that's not included on this plot at the lower end of the temperature range, you have the temperature crosses the solidus line, and there you have the biggest concentration of your latent heat right there. If we would have included that on the plot, it would have been a very large value, would have thrown these other figures way out of proportion, it would have made them illegible. That's why we didn't include it on the plot. But keep in mind that at the lower end of the temperature range in this mushy zone, you have most of the latent heat right there as the temperature crosses the solidus line for the yellow.
Oh wait, you had a plot with that on it that you showed me?
I did. I struck it in the interest of time.
Oh, okay. I mean, it was right there.
I think it's
the
in
same slide.
I think it's in the backup slides.
Okay.
Yeah.
Yeah, I really like that plot.
Okay.
All right. It was just right on the same slide. Okay.
Yeah.
You show it afterwards.
Okay, sure.
Yeah.
Here's the geometry and solver settings we use for our simulations. Keep in mind that as an symmetric simulation, the x-axis is the axis of rotation, which is why the geometry is depicted horizontally. All our simulations were 2D, transient, axisymmetric with gravity enabled. The models we used were solidification and melting, energy, turbulence with K omega. We used the pressure-based solver with pressure-velocity coupling. We used Presto, pressure discretization. All spatial discretization was second order. We also used second order implicit time. And initialization was done with hybrid initialization and temperature patching.
Are you modeling airflow or only the molten L1?
Okay, good question. So we are including the airflow, the turbulent airflow as it comes up the annulus here. Our model in Fluent doesn't actually include the combustion with the propane burner at the bottom. Our simulation starts with 1,000 degrees Celsius air flowing upwards through the annulus with the containment cylinder that contains the L.
And yeah, that was one of my other earlier questions, that this burner is just for lab scale studies because you'll have hot working fluid for the final application.
True.
Yeah, the burner simulates the solar receiver. Mm-hmm. Hot air coming out of the solar receiver is now hot air coming out of the burner.
That's what I'm confused about. What is this final thermal? How are you going to tap into this metal alloy at the end? Say at night you want to get power a turbine or something. What do you do? But once you have this hot thermal or this energy stored in the thermal alloy, then what?
Okay, like in the final system, you would then flow more air past it, just room temperature air, which would then absorb a lot of the heat being stored in the metal. And then presumably that would get your air up to 1,000 Celsius or something comparable, which would then be the input to your turbine.
I see.
Yeah, I think you have a graph showing the discharge.
True, yeah.
You'll see that. There's work to be done on that, for sure. But that's the general concept.
Mm-hmm.
Yeah, the other issue, as long as we're on this slide, that you ran into some problems with is you need to specify the same model, turbulence model, for the air and the alloy, the molten alloy, right?
In Fluent, the L is marked as being a laminar zone, so I don't believe Fluent actually applies the turbulent model there. We did have an issue. I thought the Courant number for our simulation gets very high because we have such quickly flowing air, and that could be affecting our ability to use the volume of fluid model with the alloy.
Okay. I was thinking there was some way you couldn't distinguish between the air and the alloy with some of the graphical user interface inputs. But anyway, we can talk offline about that.
Okay, sure, yeah. So here are some performance estimates of what we should expect to see, not only in experimental tests, but in numerical simulation results. First one is an estimate of the turbulent heat transfer coefficient that should be found. As many of you know, calculating turbulent heat transfer coefficients is very rough. They're usually based on experimentally determined correlations. It's far from exact science. We took 5 of these correlations and we evaluated them all. I'll present 2 of them here kind of as an upper and lower bound of what type of turbulent heat transfer coefficient we should be finding. The first one is Colburn's famous empirical correlation that relates the friction factor of a duct to the heat transfer coefficient. The original formula is there. You can see if it's expanded, rearranged, and solved for H, that's the expression. And for values that are representative of a eutectic alloy melt for us midway through the melt, you would expect to find an H value of about 309 watts per square meter Kelvin. So Colburn's empirical correlation gives us a reasonable upper bound on what type of H value we should be finding.
What is ST?
ST is the standard number, which I believe is the Nusselt number over the Reynolds and Prandtl number. Yeah, it's another way of expressing the heat transfer coefficient. And then another correlation we used, Cedar and Tate's correlation. Their formula is shown there. Plugging in the same values we used for Colburn's correlation, you get an H value of about 151. So we would expect to find an H value from Fluent of somewhere between 151 or 309 or somewhere around there. Once you have an estimate for your turbulent heat transfer coefficient, you can start estimating the overall heat transfer, and so the total time it would take your alloy to melt. As you might remember from earlier, we estimated the total energy that would be required to heat the concrete shell and internals in order to melt the alloy would be about 8.7 megajoules. 250, you can then determine the amount of heat, combustion heat, that's being removed from the air and applied to your annulus. From that, you can estimate the total heat transfer rate, and with the 8.7 megajoules figure given earlier, you would find approximately 50% of that combustion heat is being absorbed, and so the total melt time could be approximated as 790 seconds. This is not an exact analytical solution. It's based on very, very rough approximation and ballpark estimates, so this should only be taken to be accurate to within an order of magnitude. Okay, before getting into the actual results, I'll describe exactly what was performed during these tests. We ran tests for all four of the alloys I described earlier. The melt test was initialized to room temperature, and then 22 grams per second of 1,000 degrees Celsius air was run through the annulus until the alloy liquid fraction reached 1, that is, until it was completely melted. For a freeze test, we initialized it to 1 degree above the liquidus temperature of whichever alloy we were studying, and ran a flow of 21 grams per second of room temperature air through the annulus until the alloy liquid fraction reached 0. And I bring this up just to remind you that for a melt test, we started at room temperature, and we went all the way up to the liquidus temperature, but for a freeze test, we start at the liquidus temperature, and we only go down to the solidus temperature. So the freeze test will happen much quicker here than the melt test. We ran some simulations with natural convection disabled. When I say that, I mean the volumetric thermal expansion coefficient was set to 0. We ran some tests that varied the air flow rate to evaluate the overall efficiency of the apparatus. We ran several tests that varied the mushy zone constant from our standard value of 10 to the 8th to a low value of 10 to the 5th to see what effect that would have on the overall simulation and the results. We performed some mesh and time step studies to verify that the solutions we were obtaining would be independent of the resolution of the mesh and time steps. You can see the results of them on the right there. These were performed on melt tests of eutectic alloy based on the total time for it to melt. Based on these results, we chose a time step of 1 second and a mesh size of 47,000 cells, which works out to about 1 millimeter cells in the annulus, containment cylinder, and outlet. So here are some of the actual results of our numerical simulations. These first plots show the liquid fractions that were calculated during melt and freeze tests, liquid fractions over time. You might notice from the melt test the time for the eutectic alloy to melt is found to be 849 seconds, and that's definitely in the same ballpark with our rough estimate earlier of 790 seconds. So that gives us some confidence that Fluent is producing accurate results. You'll also notice that the hypereutectic alloys each take successively longer to melt, and that's because they each have successively higher liquidus temperatures. The freezing tests behave slightly differently, and that's because they each have different initialization temperatures, and they have different mushy zones we need to go through. They also form a horizontal asymptote towards the end of the test, and that's because they're encountering that solidus line, which holds the bulk of the latent heat of fusion. And that's why the freeze tests seem to drag on for so long. Here are contour plots, snapshots in time of the temperature and liquid fraction gradients during the detected melt test. You'll notice each alloy melts from the bottom to the top during a melt test, with the exterior a little ahead of the interior, since there's a lot of heat coming from that aluminum containment cylinder. You'll also notice that the temperature contours here are slanted, and that's due to the flow of natural convection. When we reran these tests with natural convection disabled, those temperature contours were straight up and down.
Can you just walk us through one of the four, set of four images, so in
Okay.
time, just to make sure everybody gets it.
Okay, sure. So these are 4 snapshots in time that show not only the temperature but the liquid fractions in the containment cylinder during one of these tests. As you can see, the top one is at 200 seconds, the next step is at 400 seconds, then 600 seconds, and then by 850 seconds, the sample had melted, so we terminated the test at that point. You can see from the liquid fraction here, red indicates liquid fraction of 1, completely liquid, and blue is a liquid fraction of 0, still completely solid. So as it starts out towards the beginning, most of the alloy in the middle of the apparatus is still solid, but you can see it's slowly melting from the bottom up, and it melts a little more with each time step until it's completely melted by the end. And you can visually compare that with the temperature gradients to see how the temperature distribution changes over time.
So you just make sure everybody knows where the containment tube is, and just, they haven't seen these before, so.
Okay, sure, yeah. As you might remember from the earlier depiction, this geometry is modeled horizontally because the x-axis is the x-axis of rotation. So the base of our containment cylinder, the aluminum containment cylinder is right here. You can see that blue curved line. That's the curved base of the containment cylinder, and it runs all the way up here. That's the top of the containment cylinder, and the outlet of the annulus is then there at the end.
Gravity is horizontal?
Gravity was enabled in the direction you'd expect gravity to go, which in this depiction is to the left.
So they're on their sides right now because it fits the slide better.
Is the temperature, sorry,
Cool, sorry, go ahead.
is the temperature 750 K Celsius or Celsius okay? Celsius, right?
Kelvin.
Kelvin, I see, I see.
So
So-
fluid sticks the K down there in the bottom.
No, because you had your melting temperature in Celsius, it was 580 Celsius, right?
That's true.
Oh,
Yeah,
I
so
see.
this is
Yeah.
in Kelvin, which kind of, I was seeing 750, I was thinking, hey, it should melt.
True. Yeah.
Good point. Thanks.
Yeah.
Okay, similarly for a freeze test, these are temperature and liquid fraction snapshots in time. These start from temperature or a time step of 0 seconds. As you can see, it's still all liquid at 0 seconds, and then it slowly begins freezing. In contrast to the melt test, you'll notice that it starts freezing from the outside. The entire outside layer freezes first, and then the interior follows after that.
For the heating process, the melting process, how hot does the concentrated solar receiver working fluid get typically?
I'm sorry, can you say that again?
How hot is the working fluid in the real solar concentrator?
We're trying to get to 1,000 centigrade.
Okay.
In the lab scale unit, we got somewhere around 900.
Okay.
But that's the hotter the better.
Right.
I don't know. Yeah.
Interesting.
It depends on, it's limited by when the particles oxidize, the carbon particles.
In air?
In air,
Okay.
yeah. And so we're still tackling. Nick is working on the particle generator to characterize the size again. And so I don't know when we'll actually measure oxidation rates. Maybe Nick will do it, maybe someone after him. Can you go back to your previous one and just point out what would you expect to happen if you did allow that to sink? The solid is not sinking now.
That's true, yes.
Right, so how would you expect those to be different?
Well, yeah, liquid fraction would obviously, the solid would continually sink, it would stay at the bottom. And I guess you'd see it slowly melting from the top down then. For the temperature contours, That's an excellent question. I think you would,
Yeah, I really meant more the liquid fraction, but
Oh.
yeah, I'm not trying to put you on the spot. I just wanted them to grasp that that spear-shaped thing would actually be sitting way over on the left.
okay, yeah, good point.
Yeah,
Yeah, this would, if solid sinking was
Enabled, yeah.
capable, this would not stay at the top, it would continually just rest at the bottom.
right. And so you took the question a little further, yeah, what would the temperature profiles do? We think about
It
that.
seems like it'll speed things up.
It would
I think
slightly
it-
speed things
I
up.
think it probably would, yeah.
Yeah. You have like a convection within a convection.
Yeah.
Yeah, I looked at, a researcher studied this a lot. Yeah, that warmer fluid, it would start to, it would pool up on top, it would start to like, it would convey a little extra additional heat transfer and convection all around the solid, not just from the bottom up.
So you're gonna be giving this as a homework problem, right? As we discussed this semester.
Yeah.
Convection. It's a great convection problem. Huh? Convection within convection.
We're now at 3:03 p.m. I don't know if you want me to speed up. There's a few slides left.
Yeah, we started a little bit late, not a lot. So yeah, please, I can try and finish it up.
Okay.
Reasonable.
Okay, here are some depictions of the air temperatures as calculated by Fluent at the outlet of the annulus. You can see them for melt and freeze tests over time. For the melt test, the temperatures, oddly enough, all overlap. And since this involves the interplay of many different factors, it appears to be a fortunate coincidence. You know, Dr. Miller saw this and kind of raises an eyebrow, but we're not really convinced anything, at least I'm not convinced anything's going wrong.
Anything's wrong, yeah. I just, it seems odd that all four alloys would give you the same result and they have different thermal properties, but yeah.
True, yeah,
If
yeah.
anybody here has some thoughts on that.
True. And the freeze test results, you can see, they're all a little separate because they're all initialized at different temperatures. But another important result from the freeze test is that none of these are actually isothermal outputs. Even the eutectic alloy changes temperature by about 200 degrees over the course of the test. So yeah, it's definitely not safe to assume we're getting isothermal output from this apparatus.
Could it be related to latent heat that you have to overcome?
Yeah, there's some dominant thing in the system that's,
Right.
yeah.
It's just do a lot of work for latent heat, right?
Yeah,
So maybe all
and so maybe,
aluminums have the same.
yeah, I wrote down a note, well, we didn't see the log plot because you took it out, but
Okay.
how different is that log plot for the four different alloys? That was
It's-
the question I had.
It's comparable. It's like 2/3. Let's see, I could.
Well, why don't you finish up and then we'll go to the log plot so people
Okay.
can see it. Yeah.
Okay, sure. Okay, here's another plot depicting the heat rates directly into and out of the alloy. This would be from the aluminum containment cylinder. For the melt test, again, they all are close to overlapping. For the freeze test, they're 1, 3, or 9. So that again gives us some confidence that Fluent is producing realistic results.
How was heat rate defined? Like, what is heat rate?
The heat flux from the aluminum containment cylinder to the alloy times the surface area.
You know, you integrated over
So you're saying that once they have the same temperature, there's no more heat transfer? Like, when the temperature equilibrates, that's when the heat transfer stops?
There would be no heat transfer if they were the same temperature, yeah. Although they are very similar temperatures, as you can see from the temperature plots earlier, there's still a difference here. There's still heat flowing. We ran several tests that varied the air flow rate in order to evaluate its effects on the efficiency of the apparatus. The question that we're asking ourselves, would decreasing the airflow rate mean more combustion heat is absorbed, and so the apparatus is behaving more efficiently? We started by defining the efficiency as the change in enthalpy of the alloy over the total heating value of the propane that was supplied. And when we ran these tests, we found, on the whole, that slowing the airflow rate only has a little effect on the efficiency. If you were to slow the airflow rate from the standard 1,000 liters per minute, to 200 standard liters per minute, you would use 12% less propane, but it would take over 4 times as long to complete a melt. The next couple slides help illustrate the role of natural convection in these melts. That plot there depicts the maximum alloy within the alloy during one of these tests. We found that natural convection on the whole played only a small role during the melt test. It would produce that flow, that velocity we expected to see. We found it produced no significant change to the overall heat transfer. When we reran the test, disabling natural convection, it didn't significantly affect the melt times overall. And we also noticed that natural convection only produced flow. It didn't produce flow in the mushy regions of the alloys, only in regions that were completely liquid. And that was for both values of the mushy zone constant that we used.
You expected to have flow in the mushy region?
We weren't sure. Other researchers have seen that. It probably depends a lot on the conditions of your problem exactly. For the higher value of the mushy zone constant, I didn't really expect to see that because then that inhibits motion in the mushy zone very much more. Lower value, I thought maybe we'd see it. We didn't. But I wasn't convinced anything was going on. Here's a contour plots, more snapshots in time, of the axial velocity profile in the alloy during the melt. And this can help you see how natural convection plays out. In the middle of each snapshot, you can see a depiction of the entire containment cylinder. And then at the bottom of each one is a zoomed-in region for easier viewing. You might notice from looking closely at these plots that conceptual dividing line between that rising outer ring and the cooling sinking core happens at about 9 millimeters for all alloys at all times. And that was a little smaller than we expected. The equidistant dividing line there would be at about 11 millimeters, and that would produce equal cross-sectional areas for the rising outer portion and the cooler sinking portion. And because of that, the cooler sinking portion is actually smaller and it moves 3 to 4 times as fast as that rising outer ring. Okay, mushy zone constant. We ran some tests that varied the mushy zone constant, but we found for our problem that varying the mushy zone constant had very little effect on the overall results. When we lowered the mushy zone constant from the default 10 to the 8th to 10 to the 5th, we found that it produced slightly faster melt times and a slightly faster alloy flow velocity. It also resulted in a larger region of flow within the alloy, but it was still only in liquid regions, not in mushy regions. And that means, oddly enough, that varying the mushy zone constant for our test didn't actually produce a difference in the mushy zone, only the liquid zone. And we found the effects of this were strongest for the most hyper-eutectic alloy, aluminum silicon 40. We also found that varying the mushy zone constant had no discernible effect at all when we also disabled natural convection. So here's a summary of the results for the models we ran. We found the results on the whole are comparable to the analytical estimates we formed at the start, and it gives us confidence that these are realistic results. We found that due to the lack of close contact melting, the times that are listed here should be treated as an upper bound for experimental tests. They may very well happen faster due to close contact melting. We found that the air outlet temperature is definitely not isothermal for any of the alloys. We found that varying the airflow rate had only a little effect on the overall efficiency. We found that natural convection produced flow, but no significant change to the heat transfer in these melt tests. We found that varying the mushy zone constant had only a small effect on the natural convection, and it only applied in liquid regions, not mushy regions. Here's some overall conclusions from this presentation and thesis. Thermal energy storage should now be considered essential for concentrated solar power. That's because it's necessary to alleviate the duck curve instead of exacerbating it. Aluminum silicon holds much promise as a high-temperature latent heat thermal energy storage solution. We're not the only researchers to feel this way. A lot of researchers feel that aluminum silicon is the alloy with the most potential for latent heat thermal energy storage. Many modifications and improvements were completed for this lab-scale apparatus during the course of this research, but it's not yet fully functional. That aluminum containment cylinder will need to be rebuilt and replaced with everything reassembled. The numerical simulation results here have helped form time estimates for experimental tests. Melt tests should be expected to take no more than 15 to 30 minutes, depending on the element. And future work that's possible for this project, the greatest value will be in completing the apparatus and running experimental tests with it. An incoming lab member is currently redesigning the aluminum containment cylinder, which is the only component needing repair. Should a new apparatus be designed in the future, it could include metal fins added to the exterior of the containment cylinder. That would improve the overall heat transfer and conduction, and so the overall efficiency of the apparatus. I should just add that there doesn't seem to be a need to redesign the apparatus, but if one is designed, these are potential changes that could be made. The output temperatures could be stabilized by slowing the airflow rate during free runs or by preheating the air. Again, this is if producing isothermal output from this apparatus is a high priority. Those are a couple of options to get closer to isothermal output. And future numerical simulation work could also attempt to include solid sinking behavior and close contact melting. It's not clear if that will be possible through Fluent or COMSOL. It may require the implementation of a custom solver. That wraps up this presentation. I'd now like to open up to any questions. Okay, hey, Nick?
Yeah,
Okay.
I have a question.
Sure.
Does the alloy, does the crystallinity change at all after you melt it and freeze it again?
That's a great question. That's a good materials question. I didn't look into that too much. I don't believe it changes much from I would get the feeling because one of the studies I quoted earlier found that there was not much phase segregation. Aluminum silicon 17 kept 96% of its latent heat capacity even after 1200 thermal cycles. That leads me to think like structurally it's not changing much, maybe a little bit. Good question. Nick?
Hey, can you explain more why you decided, or how you were able to switch to the smaller caps, or the smaller end plates?
Okay, sure. So one of the big insights was that the thermal behavior of the internals wouldn't change that much. And that can be broken down to a few different components. First of all, like combustion heat that's produced by our burner and the mass flow controllers. The mass flow controllers regulate the mass flow rate. Okay, obviously that wouldn't change with a change in pressure. The burner combustion of propane, if you work out the math, it's about the same temperature. It differs by like 0.1% temperature-wise between 1 atmosphere of pressure and 5 atmospheres of pressure. And then the heat transfer from that airflow to the annulus also wouldn't significantly change with the change in pressure. And because you can realize that by keeping in mind the Colburn correlation I used in one of the studies. That relates the friction factor of a tube to the heat transfer coefficient. For us, it pays to keep in mind, well, the geometry certainly wouldn't change with the change in pressure, but then also your Reynolds number wouldn't change with the change in pressure. And because of that, the overall friction factor wouldn't change. And because of the Colburn correlation, then your overall heat transfer coefficient wouldn't change. So in short, when you take all these different considerations together, it means that the overall thermal behavior wouldn't have any significant difference from 1 atmosphere to 5 atmospheres. And that, to me, is a good enough reason to use much lighter lids.
How much lighter are they?
They're like 20 pounds or something. Yeah, the old ones were 90 pounds.
Can you lift that?
Yeah. I'll call Alvin if I have any trouble. Hey, Phil.
My question was why the mushy zone was considered an issue in implementation, and I was guessing it was because for actual applications, you'd have, say, flow going into a storage device or something of that nature, and you'd have cooling of, say, fluid that was inconsistent, and that would cause thermal stress or something. And I guess why was that an issue? I guess that was the question.
Okay. Yeah, let's see. So the mushy zone is a significant temperature region for all our off-eutectic alloys, and it's being modeled inaccurately by Fluent in the enthalpy porosity method. If you remember that chart I showed earlier, like the enthalpy porosity method uses just that straight linear line. Yeah. And so anyway, because that significantly affects the latent heat distribution, which is a pretty central part of our study here, the thermal behavior of this alloy. And so because it's modeled so inaccurately by Fluent, we looked at ways to work around that.
Oh, so it's more of a known issue from the beginning for your models. I see.
Yeah.
When you first brought it up, I think because I was trying to physically visualize what that looks like in flows. That's what I was. guess what that is. That
Okay.
makes sense, thank you.
Yeah, it was all thermal stuff, had really nothing to do with stresses or anything.
I see.
Can you bring up your log plot?
Yeah, I think so, hopefully.
I want to see that log plot. Oh. Yeah, actually go back.
great plots.
There,
Yeah.
there you go.
Through convection, it prompted melting of a hollow cylinder from its center to the outside. Here's some more math on the exact problem and its solution. You can see the geometry for the problem. It's a hollow cylinder, so keep in mind that portion through the center is hollow and then gradually melt from the inside out. The energy equation, you might notice, is the steady state energy equation for conduction in radial coordinates, but also has that moving melt front, that moving boundary condition, and that's the quasi-steady approximation. Because you're assuming the sensible heat is zero, the temperature wouldn't change with time, only the amount that is melted. And so that, I guess, displays the quasi-steady approximation there. You've got some boundary conditions and interface conditions that are probably familiar to a lot of you from similar convection problems and conduction problems. The textbook we're using found the analytical solution as this. I'm glad we were able to find this in textbook and we didn't have to work it out for ourselves. And then the melt front, S, is obtained from the solution to this, the following transcendental equation. With that in mind, that's the analytical solution for our problem. When implemented in Fluent, we then perform mesh and time step studies on it, varying the resolution of the mesh and the size of the time steps in order to try to get a solution that we felt was independent of the resolution of the mesh and the time steps. So you can see in both of these plots, as you go from left to right, finer and finer meshes and smaller time steps, the results that Fluent is producing start converging approximately towards the analytical solution. And once it gets close enough, we start to feel like, okay, this is not, if we use a finer mesh or a finer time step, this isn't going to wildly veer off course. These are starting to produce good results. And that's the point of the mesh and time step studies we did here.
Other question?
I want to see that log plot.
Yeah.
By popular demand, I'll put it up.
Is it in your thesis?
I could put it in my thesis.
No.
Yeah, I think it should be. but,
Okay.
Yeah.
Look in the recycle bin.
Are you trying to find the comment, the one that I commented on?
No, I put
You
it
have
in there.
Okay.
And so I'm just kind of trying to keep track of all the, it's loading. My computer's so slow, it takes.
Yeah. The versions. There it is.
Oh, there's setting log plot. That's the large spike that I was describing earlier. As the temperature crosses the solidus line, most of the latent heat is stored and released. In our case, we spread that latent heat across a 10-degree temperature range, so Fluent didn't have to try to build it across a single temperature that could have made it much difficult for Fluent to converge. And the number here, I believe, is about 49,000 joules per kilogram Kelvin, which is pretty significant.
You just click back once you can see the original plot. There.
Okay.
That's what he showed during the defense. And then the next plot is the log. It's the same data, just with a semi-log, so you can see the huge spike. But so that's for AI, or ALSI, excuse me, 40.
Yep.
That spike occurs at the same place for all the alloys?
I could bring up the, I produced plots of all four of those.
I'm wondering if that might be why all four seem to behave the same. If it's dominated by that spike, is it always at the same temperature?
They do have a spike like that. at the same temperature range. It's not the exact same number.
Not
but
exactly.
It's a large
Well,
spike for all of them.
Yeah, so maybe if it's if the temperature for all of them is close, maybe that's why all four behave the same?
That could
Maybe, I don't know,
That's true.
that's very much puzzling to me since I first saw that graph. But
Yeah,
it doesn't matter which alloy you use, you get the same air temperature.
if you look at the numbers for the material properties for a lot of these alloys, and you, I'm trying to think of the plot. There's a plot where they behave significantly differently. I think it's an actual convection plot. And the reason behind them behaving significantly differently is not that they have significantly different material properties like this. It's because they assume sharper temperature gradients. Just give me a few slides, I'll come up here. I put that commentary in here somewhere. Okay, so yeah, so this is the plot depicting natural convection. This is the maximum velocity in each alloy during a melt test. And you can see the eutectic, it jumps way up, much higher than any of the other alloys. And then the aluminum silicon 20, and 30, and 40, they get lower and lower. And that difference, there is no significant difference. There's little differences in like the viscosity and the thermal expansion coefficient for these alloys. But none of that should produce these significant differences in the velocity during flow. As far as I can tell, all this velocity difference is because each alloy experiences a significantly different temperature gradient. So for example, the eutectic alloy, it melts the fastest. And so because of that, it's going to assume the sharpest temperature gradient compared to aluminum silicon 40, the most hypereutectic. It takes forever and it drags on towards the end. Towards the end, there's like no temperature gradient. It's all getting very warm all over the place. So you'll see a significant temperature gradient in the eutectic alloy, and that's why that produces such a jump in the maximum velocity there.
So can you make a plot of max temperature gradient versus time for the four alloys? And
You could.
You're describing in words that, but that would, if it's linked to the temperature gradient, you should see something similar.
We
Right.
could do that.
Now, how do you know it's a higher temperature gradient just from looking at the color pictures?
Looking at
basically?
the temperature gradients, I can show them in the backup slides. The temperature gradient in aluminum silicon 40, it becomes very muddled, especially towards the end of the test, and it's just like a big blur. Whereas for the eutectic, you can see those sharp temperature gradients the whole way through.
Okay.
And
Yeah.
as far as I can tell, that delta T, that's what drives such significantly higher velocity in natural convection.